welcome back. So this is the second in a series of 3 videos in which we're going to see how to find the area under a curve using calculus and Riemann sums. So the particular curve that we're working with is the function 100 minus x squared. And what we're trying to do is we're trying to find the area under that curve between x is equal to 0 and x is equal to 8. Oh yeah, it got erased, but this was an 8 here. So between x is equal to 0 and x is equal to 8. And so what we did in the last video, was we found this formula. And actually, I'm going to go ahead and change the name of this formula. I called it F before, but why don't we call it R for Riemann sum? Because what this formula is going to tell us is if you tell me what n is, and you plug it into this formula, and you evaluate the sum, you get the area of the Riemann sum. So as an example, if we used 16 rectangles, so here you can see this is a right Riemann sum. Here's a picture of a right Riemann sum for the area under the curve using 16 rectangles. And GeoGebra tells us that it's about 613, and I promise you that if everywhere you see an n in this formula, if you put a 16 and then you evaluate this sum, you will get 613. So in some sense, this is what GeoGebra is doing. When GeoGebra finds this number, it essentially is doing this summation. All right, so that's what we did in video 1. And so now what we're going to do in video 2 is we're going to use algebra so we can simplify this formula so that we don't have the summation anymore. Because the summation is nice, but the summation, what it's doing is it's hiding potentially thousands of additions. And so if you're using a computer, then that's no big deal because computers can add thousands of numbers together very quickly. But what we want to do is we want to try to use algebra to simplify this so that the summation is not there anymore, so that there won't be thousands of computations hidden behind the scenes that a computer could do that we couldn't. So we want to simplify this formula so that it's in a form that you and me can actually use practically. I guess because you and me could both we could add thousands of numbers together. It would just take us a very long time, and so we don't want to do that. We want to simplify it so we can do it faster. Okay, so what we're going to do here, this is just all algebra. So I got rid of all the pictures, I got rid of all the stuff, and now we're kind of just going to be in pure algebra mode here. So the first thing I'm going to do here is remember that this is a constant. The only thing, now again, it might be confusing here because there's 2 variables. You can see that there's a variable of n. And actually, I'm going to change the n to red because the n is a different kind of variable than I. So n is a variable and I is a variable. But within the context of this problem, we're thinking about n as a constant, right? Because you're telling me how many rectangles to use. Like you're saying use 1,000 rectangles. So if you say use 1,000 rectangles, then n is 1,000. So n is actually a constant. I mean, it's an unknown, but it's actually a constant in the context of this formula. Whereas the I is the index, and the I is definitely changing. The I starts at 1, and then it turns into a 2, and then it turns into a 3, until it gets up to whatever n is. So the moral is that this 8 over n, even though it might look like it's changing, it's actually a constant. It has nothing to do with I. So by the rules of summation algebra, I can factor that out, right? You can always factor constants out of your summation. So that's a legal algebraic move right there. And then, let's see, so then what's left? Okay, what's left is I have a 100, and then I have a minus 8 over n times I squared. And I'm going to reserve the color yellow for the i's. Okay, so I have that. And now if you think, I guess maybe I probably should put parentheses there, just to be clear. So now if you remember, another property of sums is, remember that the summation can distribute over addition and subtraction. So what we can do here is we can rewrite this as, okay, so we got the 8 over n is in front, and then a big parenthesis, because this 8 over n is getting multiplied by everything. So I need to make sure that I don't forget that. And then now I'm going to have the sum from I is equal to 1 to n. And I'll write the I is equal to 1 later because I need to change colors. And then there's a 100. And then I subtract. And then I have the sum again. Because basically what we said is the sum distributes over addition and subtraction. And then here we'll have 8 over n, and then squared. And now I can change my color and put in, finish writing the things here. I is equal to 1, I is equal to 1, and there was an I there. All right, so what happened in that step was simply that we used summation algebra to distribute the summation over the subtraction that was right here. Okay, so now let's think about what we got here now. This is just the sum of a bunch of 100s, right? This is, remember when you did this, and I'm sure you've done problems like this, but remember what this is saying. What this is essentially saying is, okay, well, you take I is equal to 1 and you get a 100. And then you take I is equal to 2 and you get another 100, because there's no I here. So no matter what I is, you always get 100. So what this sum turns out to be is, this is like a 100, and then I is 2, and you get another 100, and then I is 3, and you get another 100. This is just a whole bunch of 100s being added together. And how many 100s are added together? Well, you start with 1 and you end with n, so this is just 100 n's being added together. And so if you think about, well, what does that mean? If you have 100 n's and you're adding, sorry, I said the wrong thing. If you have n 100s and you add them all together, then what you have is you just have 100 times n, right? Like, because if n was 16, if you have 16 100s added together, then you get 1600, which is 100 times 16. So this summation, I hope that made sense. If that didn't make sense, go back and review summation properties. And so this just turns out to be 100 times n. And then now this guy, okay, so well, let's make a new line here. And record all of this. So, okay, so we've still got the 8 over n. And now we've decided that this summation we can make completely go away. And that's just going to be turned into 100 multiplied by n. And then we have subtract the sum from I is equal to 1 to n. And why don't I go ahead, I want to get rid of these parentheses. So to get rid of these parentheses, I have to square both things inside. So 8 squared is 64. And then n squared is, well, that's just n squared. And then you'll have I squared. So if I square, and then this is the sum from I is equal to 1 to n. Oops. So this sum, what did I do in that step? What I did in that step was I replaced this summation with what it was actually equal to, because this was an easy summation to do. And then with this summation, I just squared both things inside of the parentheses so that I could get rid of this set of parentheses. So 8 squared makes 64, n squared is n squared, and I squared is just I squared. And now when I look at this, so there's only one summation left. And so when I look at this now, I can say, hey, this red thing, this doesn't have anything to do with I, which means that this is a constant. Because again, we're imagining that n is a fixed number. So if n is a fixed number, then this is a constant. So great, I know that constants can get factored out of my summation. So my next step is 8 over n times 100 n minus, okay, the 64 over n squared can now get factored out. And then you have the sum from I is equal to n, from I is equal to 1. You have the sum from I is equal to 1 to n of I squared. And I'll close that parenthesis. And there we go. Okay, so we're really close. So hang it. If you're still hanging in there, you're doing great. So this is the part where I kind of have to cheat just a little bit. And when I say cheat, I mean use sort of a formula or an idea that we haven't really proven or that we've talked about. But let's look at this guy again. The action is all right here now. Because again, our goal was to get rid of the summation, and now we're sort of, the buck has stopped here. We've factored out everything that we can possibly factor out. Everything that's left has an I in it. So we're sort of stuck here. So let's think about, what does this really mean? If you think about what this really means, this is, well, let's just see if we can figure it out. It says I is equal to 1, and then you square it. So this is 1 squared. Okay, but then you increment I, so I is now 2, and then you square it. And then you increment I again, so you get 3, and you square it. And you keep doing this until you get to n. And you get n squared. So basically what is sitting right here is the sum of the first n square whole numbers. Or the first n whole number square whole numbers. So it's like 1 plus 4 plus 9 plus 16 plus 25 until you decide to stop. And so, you might think mathematicians, this seems like it might be kind of an important number. Mathematicians at some point have probably sat down and wondered, hey, what is the sum of the first n squared whole numbers? I think I said that wrong. What is the sum of the first n squares? That's what I should say. Or what is this sum here? And so mathematicians have actually figured that out, and there's a formula. And so actually here it is right here. That if you want to add up 1 squared plus 2 squared plus 3 squared all the way up to n squared, there's actually a nice simple formula for that right here, which is really pretty amazing. So good job to all the mathematicians who figured this out. But this is a real nice little formula here. So we can put that to use in this problem. So let me go ahead and do that. So I'm going to slide this off of the screen, but you can pause the video and write it down in your notes. And so now, let's get back to our sum here. So what we've got now here is we've got 8 over n times 100 times n minus 64 over n squared. And now this crazy summation that we had, we can now replace it by that formula that the mathematicians discovered. And that's what I mean by cheating a little bit, is that we're using a formula that other mathematicians have discovered. We didn't really discover it ourselves, and so we haven't actually proven this. And so essentially you're trusting me that this formula is true. And I wouldn't lie to you. So you can trust me that this formula is true. And if you're interested, you can stop by my office sometime and I can prove it for you. Or you can watch their videos online of this being proven. It's not super hard to prove, but it's not something we want to do right now. Okay, so this is great. This is actually really exciting what just happened now, because think about where we started. Where we started was right here. And if we wanted to use 1,000 rectangles, then we would have to replace the n by 1,000. And when we use this formula, we would have to add together 1,000 numbers. And a computer could do it, but we can't. But now look at this. If I want these are the same thing. What this algebra shows is that the two things that I've circled are exactly the same thing. And the advantage to this is now if I want to set n equal to 1,000, I can just do that. And I can do that with a few presses of buttons on my calculator. This is just a formula. It's kind of a messy formula, but again, think about this. The one we started with involved adding 1,000 things together, potentially, if n was 1,000. If n was 1,000, I'd have to add 1,000 things together. Whereas in this formula, all I have to do is put 1,000 wherever I see an n. And sure, I get a crazy number, but with a calculator, I could figure that out in a not too long at all. And you might say, oh, wait, Travis, I thought we weren't using calculators. And well, okay, yeah, you're right. I guess even if I didn't have a calculator, I could put n is equal to 1,000 in there, and it would be a mess, but it would just, I would just have to do some multiplications. I would have to do some divisions. But it's totally doable. And in fact, we can simplify this some more. So why stop there? Let's try to simplify this some more. All right, so I'm going to erase all this stuff that I don't need, and then we're just going to focus on simplifying this. Okay, so I got rid of all that stuff that I don't need, and now we're going to focus on simplifying what I have in the box here to get an even better answer. So so there's a multiplication happening on the outside here. So let's go ahead and distribute that multiplication. So the multiplication distributes over the subtraction. So let's see. Okay, well, 8 over n times 100 times n, well, the n's will just cancel, and you just have 800. So, all right. So we're just going to have 800, and then we'll have minus, okay, 8 times 64. There's a good question. What's 8 times 64? And so 8 times, we got 8 times 64. 8 times 64 is, did I give you enough time to think about it? I think it's 512. It better be, because I really don't want to make a mistake. So 512, and then let's see, divide n times n squared makes n cubed. And then we've got this yellow fraction here, and I'm going to go ahead and do FOIL in the numerator. So let's see here. So we're going to get, n times 2n. That makes 2n squared. And then there's going to be an n times 1, and then a 2n times 1. So that makes a total of 3n. And then 1 times 1 makes 1. Oh, wait, but not so fast, because I forgot you also have to multiply by this n. All right, so basically all those powers are gonna get bumped up by 1. So that should be an n cubed, that should be an n squared, and that should be an n. So this will be an n squared. That'll be an n cubed. And so that's what, if you do FOIL, you should pause the video and go through that yourself to verify that that's correct. But when you do FOIL to that numerator, when you multiply out all that numerator stuff, that's what you get. And okay, so let's keep going. Let's simplify it even a little bit more. You might say, at this point, it's really pretty good. But the next video will be even easier if we do a little bit more simplification. So, all right, so now we've got 800, and we've got minus 512. Well, let me think about this for a minute. Oh, yeah. Shoot. So we got these fractions, we got these constants. We got the 512 and the 6, and 512 divided by 6 is not a whole number, but 2 divides 512, and 2 goes into 512 256 times, and 2 goes into 6 3 times. So the 512 over 6 can simplify to that number. And then what we've got is we've got the 2n cubed plus 3n squared plus n, and then we're dividing by n cubed. And so, okay, I'm almost done. So my final simplification, my final answer, which we'll put up here, is going to be 800 minus 256 over 3, and then multiplied by, okay, let's see, 2n cubed divided by n cubed is just 2. 3, and then we'll have plus 3 over n, because, n squared divided by n cubed is 1 over n, and then plus 1 over n squared. Okay, and I will circle that, because that is going to be my ultimate simplification. And that is, I think, so what is this? So this is a form, yeah, it's important to keep track of where we are and what just happened. So what happened is this is the formula that will tell you the area. So let's go ahead and test it out. So I'm going to erase everything except this formula, and then we will test this formula and see that it actually works. Okay, so what we got here is this. This is the formula that we found after simplifying our other formula. And so the claim is that this will do the same thing that our other formula did, but we don't need a summation anymore. So the claim is that if you tell me how many rectangles to use, and I put that in for n in this formula, then I will get the area of the Riemann sum. So as an example, let's look at two examples to make sure this formula works. So I have the formula programmed here in Wolfram Alpha. And so as a test, GeoGebra says that when you use 16 rectangles, the right-hand Riemann sum is 613. So all right, so let's go to this formula, and wherever I see an n, I'm going to replace it by 16. So wherever I see an n in this formula, I'm replacing it by 16. Well, and there you go. You can see it right there. GeoGebra tells us, or not GeoGebra, Wolfram does this calculation, and when Wolfram does this calculation, it gets exactly 613. So again, this is amazing. This is really awesome, because suppose I jack this up to 50. So GeoGebra can do this, because GeoGebra is smart. But I wouldn't want to have to do this myself. Adding up all 50 of these rectangles, that would take me all day. But using this formula, that won't take me long at all. Just everywhere I see a 50, everywhere I see an n, I put 50. And let's see here. So GeoGebra tells us the answer should be about 624. And then Wolfram tells us that the exact result is this, which is about 624.18. So they're the same. And in fact, this formula is better than GeoGebra, because GeoGebra is giving us an approximation, whereas this formula gives us the exact answer if we want it. So what just happened? What we now have is a very compact formula that if you tell me to use 1,000 rectangles, then all I have to do is put 1,000 into this formula, and I will get the area under the 1,000 rectangles. If you tell me to use 1,000,000 rectangles, no problem. I will get this formula will give me the area under 1,000,000 rectangles. So we're now ready to make the final step, and that final step will give us the area, the exact area under the curve. So again, remember, that was our ultimate goal. Our ultimate goal was to find the actual area under the curve, and we are now in position to do that. And it'll be really easy. It'll be so easy you won't believe it.